Welcome to video lecture D4. This is on Cramer's Rule. I'll be your DM, Tom Roby. Our outline and objectives are to derive a simple theoretical formula called Cramer's Rule for computing solutions to an n-by-n system, ax equals b, using determinants. And then we'll utilize this to prove a simple rule for computing the inverse of an invertible matrix in terms of its determinant and a matrix of cofactors, which we'll call the adjugate. So here's Cramer's rule. If I've got an n-by-n matrix and a vector in Rn, then I'm going to define ai of b to be, think of A as a matrix of column vectors. So I've got a1 through an, but I'm going to replace the ith column vector with my vector b. That's what ai of b means. And what Cramer's rule says is that in this situation, the unique solution to ax equals b is given, well, I need to tell you what each of the xi's are in the vector. It's given by just taking the determinant of ai of b divided by the determinant of a. And I have to do that for each possible value. Let's look at an example right away to see what's going on. So here's a system we've seen before and solved before, and its matrix of coefficients is 3, 2, 5, 4, right? So there's 3, 2, 5, 4. That determinant is 3 times 4 minus 5 times 2, so that's 12 minus 10 is 2. And now, up here, to get x1, I replace the first column with my matrix B, the output I'm trying to get. So instead of 3, 5, I have minus 1, 3. Keep the 2, 4. Take the determinant of that, I get negative 4 minus 6 is negative 10, divided by this determinant, which is 2, and I get negative 5. So that's x1. And x2 is, replace the second column by b, which is negative 1, 3, and take 5. That determinant is 3 times 3 minus 5 times minus 1 is 9 plus 5, which is 14, divided by 2 is 7. Okay, so that's the solution to this system of equations. And the proof is only a couple of lines. It just takes a minute to unpack what's going on. So here's what I want to do. I'm going to take this definition, ai of b, and apply it to the identity matrix. I'm going to take the n-by-n identity matrix and replace the ith column with x. There's nothing to stop me from doing that. And now let's see what happens when I multiply a times I sub I of x. Well, what I really care about is what am I going to get in this ith column, and this ith column will just be ax, right? Because ax means take the linear combination of these column vectors given by x. And the rest of it will just be the same as it was before. Now I know that this has to be ax, if it's a solution, has to be equal to b, right? So this just becomes a1 dot 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 b an, which by definition is just a sub I of b. Okay? So all I did was look carefully at this computation and see that multiplying a times the matrix I get when I replace the n-by-n identity matrix in the ith column with x, that gives me what I get when I replace the ith column of a with b. Okay? But now I can use what we proved earlier, that the determinant of the product is the product of the determinants. So the determinant of this times the determinant of that should be equal to the determinant of this. Okay, good. So that's what I wrote here. The determinant of a times the determinant of this is the determinant of that. And you can see that what I really want to get is, I'm trying to get as output this divided by this, right? So all I really need to do to prove this, finish the proof, is to show that in fact the determinant of I sub I of x is equal to x sub I. Okay, and so how do we do something like that? Well, just analyze it, right? What does it mean if I have something like, maybe I'll take a small example. So suppose I have something, so I've taken 1, 0, 0, 0, 0, 1, 0, 0, and then I've got x1. Suppose I replaced the third column with that, and then I've got 0, 0, 0, 1, right? Okay, so the determinant of this matrix, I want to show that it's just xi. So if I expand it along the ith row, so let's expand it along the ith row now. So this was the third one, so I'll expand it. Oops. So I'll expand it along this row. So when I do that, what do I get? Well, these are all zeros, so I just have x3, maybe times a sign, and I also get rid of this column, and so I'll just have, this is just going to be equal to x3 times the determinant of 1, 0, 0, 0, 1, 0, 0, 0, 1, the identity matrix, and that's just equal to x3. So that's the idea for why x sub I is just equal to the determinant of xi of x. Right, and this, because this is always in the ith position, it's always going to have a positive sign, right? So I don't need to worry about a sign there. Okay, so that explains why this Cramer's rule is true. Now, practically, it's actually pretty hard to compute determinants efficiently. So if you're trying to teach a computer to do this to a 20 by 20 or 30 by 30 system, you're not going to use Cramer's rule. So that's in practice. But in theory, it's useful, for example, if I want to understand like how x changes is sensitive to perturbations in the value of b, having an explicit formula like this can be useful. Another application of it is later on in your mathematical career, you might see generating functions, and which are things, power series that we use to count things. And this is the key ingredient in creating something called the transfer matrix method that will let us compute generating functions that count, say, walks and graphs or things. If you ever get to watch the movie Good Will Hunting, which is one of the movies about mathematics and mathematicians from about 20 years ago, the hard unsolved problem is actually a pretty elementary first-year graduate combinatorics problem that's solved using basically the transfer matrix method, which boils down to Cramer's rule. Okay. But the other thing I like about this proof is that it reinforces a bunch of the concepts that we've been studying all along here. And so now let's generalize this one step further and say, if we can solve systems, we can probably compute inverses. Right? These things are kind of linked. And so let's define the adjugate of a matrix A. So the adjugate of a matrix is another matrix of the same size, and each of these CKLs is just a number. What number is it? Well, it's this cofactor thing again. It's minus 1 to the k plus L times the determinant of AKL. Delete the kth row in the Lth column and take the determinant of that. So this is just some number, and I arrange them not the way you might think, but in the transpose of the way you might initially suspect. So I've got C11, C12, dot, dot, C1n going down the first column instead of across the first row. I'm using the transpose. Okay? And so let's just take a quick look at an example. So the transpose doesn't matter for this one. So if I want to figure out what this guy is, I have to say, okay, this is a positive sign. Delete that row and that column. I have 1, 4, 2, 3. And that is 1, 3 minus 8. That's negative 5. So that value is clear. Now, if I want to see this 0, well, this 0 actually comes from this is the 1, 2 entry in the adjugate, comes from the 2, 1 entry in A. So I delete this column and this row. I have 2, 3, 2, 3 times a minus 1, but it doesn't matter because 2, 3, 2, 3, that has determinant 6 minus 6, which is 0. So that explains the 0. And finally, if I wanted this negative 4, where did that come from? The negative 4 comes from the cofactor based here. So I delete the middle column and the top row, and I have 0, 4, negative 1, 3. So 3 times 0 minus minus 4 is plus 4. But then I have a minus sign from the minus 1 to the k plus L because I'm in the 1, 2 position. Okay? So I computed three of those 3 entries, and you can check the rest and see that they work. So that's the adjugate. And the main theorem here is that if I take the adjugate and I divide every entry by the determinant, rescale it, then I get actually the inverse of the matrix. So it's kind of wacky that taking this matrix of determinants, taking this matrix of cofactors, making the transpose actually gives you something that turns out to give you the determinant. And so here's the proof. So what have we got? We have AY equal to the identity, right? If A is invertible, then there is some inverse, and let's just call it Y. And it has the property that when you multiply these two matrices, you get the identity. So I write them as column vectors. And now let's just make this the jth column. I just want to call it y because I want to later talk about its coordinates, so I don't want to give it a subscript right now. All right. So, and what happens when I do that? Well, since I'm saying that this is equal to the identity, that means the jth column vector here has to be the yth linear combination of these columns. In other words, ay is equal to e sub j. Okay? So in order to have the matrix Y, which is the inverse of A, that has to be true that the jth column vector Y satisfies AY equals EJ, right, where that's just the jth standard basis vector. Okay? So that means that the jth column, it's given coordinate-wise by Cramer's rule that we just saw as y sub I equals, well, a sub I of e sub j divided by the determinant of A, the determinant of this thing divided by that. So I guess the main thing we need to check here that in order to believe this is to say, well, what happens if I take the determinant of a sub I of e sub j, right? So what am I doing here? I've got, so now I want to think about columns, right? So I'll think about let's see, A1, A2, dot, 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 AN, B1, B2, dot, 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 BN. And now somewhere here, maybe I have E sub j here, right? So I've got 0, 0, dot, 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 1, and then I've got a 0. And so this is happening in row j, and this is column I. Okay? And then I keep going, and then maybe I've got Z1, Z2. Right, so these are the columns of my matrix, but I've replaced column I with this jth column vector. And so now I say, well, what happens when I take the determinant of that? So when I take the determinant of that, whoops, let's pick a color that's writing now. When I take the determinant of that, so here I am in the jth row, right? So I'm deleting this row and this column. Then what I'm left with is just the cofactor Cji. Okay? So the determinant of this matrix Cji, really just by definition, because I get what I block out this turns out to be the jth row in the ith column. Okay? So this matrix here then is just Cj, the determinant of that matrix is just Cji. So that means that that column y sub I, the jth column of the inverse matrix, has vectors Cj1, Cj2, dot, 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 Cjn. Okay? Okay, so now I'm good, because now I just need to, so then A inverse is just all these Cji's divided by the determinant of A, and so that's just 1 over the determinant of A. I can pull the 1 out of the determinant of A out of the whole thing, you get the matrix of Cji's, this matrix here, which is just the adjugate. Okay, so that's what's going on in this computation. And so the last thing I want to ask you to think about is, what should we get when we multiply A times its adjugate? So look at the theorem and think about it for a minute. Pause if you like. Well, it's pretty clear that if I multiply A, so if I multiply both sides of this by A, then I'll get the identity here, and then I'll get the adjugate of A times A, and let's move the determinant over to the other side. And so what should be true here is that, so A inverse, A times A inverse equals A times 1 over the determinant of A times the adjugate of A. And so now let's multiply. So this just becomes the identity. Whoops, you can't see that. That becomes the identity. So now that means that A times the adjugate of A is just equal to the determinant of A times the identity matrix. Okay? So let's just double check that that works in this particular case. So if I take A over here, 1, 2, 3, 0, 1, 4, negative 1, 2, 3, and I multiply by its adjugate, minus 5, 0, 5, minus 4, 6, minus 4, 1, minus 4, 1, what do I get? Well, so in the first coordinate, I'm going to do row-column version now. So I'll get negative 5, minus 4 is minus, negative 5 minus 8 plus 3 is negative 10 here. And now if I do it here, I'll get 0 plus 12 minus 12, so that's 0. And now if I do it here, I'll get 5 minus 8 plus 3 is 0 again. And now if I do this one, I'll get negative, so 0, negative 4 plus 4 is 0. This middle one, I get 6 minus 16, so I get negative 10. And if you keep doing this, you'll see that you just get this matrix, which is negative 10 times the 3 by 3 identity matrix. Okay, so that's it for video lecture D4. Thank you for your kind attention.